Hello and welcome to Physics Video Fluids Point 2. In this video, we will continue our discussion about how fluids behave in different situations. In particular, we will look at ways to measure fluid pressures, as well as how to use properties of pressures to do work for us. These topics are under the categories of Pascal's principle, gauges, and barometers. We know that the Earth's atmosphere must be exerting a pressure on us because of the weight of air. So let's talk about how much that actually is to begin with. At sea level, atmospheric pressure is about 1.013 times 10 to the fifth newtons per meter squared. This is by definition what we call an atmosphere. Another unit of pressure is the bar, and 1 bar is 1.00 times 10 to the fifth newtons per square meter. So notice that a bar and an atmosphere are very close to each other. But when we're talking about atmospheric pressure, it's important to realize that these slight differences are actually important. So as we have said, the standard atmospheric pressure is just over 1 bar. Now this pressure at sea level, this 1 atmosphere, does not crush us, as our cells maintain an internal pressure that balances out the atmospheric pressure. In other words, we evolved to survive with this amount of atmospheric pressure. Pressure gauges mostly read the amount of pressure above the atmospheric pressure there is. So we have to distinguish between whether we're talking about a gauge pressure, the pressure that registers on pressure gauges, or we are talking about absolute pressure. Absolute pressure being the atmospheric pressure plus the gauge pressure. Most of the time, it will say in the problem which one we're talking about, but our absolute pressure we typically write as just a P, and we say that it is the atmospheric pressure plus the gauge pressure. Okay, so those are two things you need to distinguish between, because you'll see that terminology very quickly in our problems. Remember, pressure is related to force. Pressure is a force per area. So that means that if we think about this in terms of the force that we're applying onto an object, we may also have this pressure, this force that we apply, do work for us. So let's look at how pressure can do work for us and what type of work it can do for us. Pascal's principle says that if an external pressure is applied to a confined fluid, the pressure at every point within the fluid increases by that amount. So external pressure increases everywhere throughout. This principle can be used in hydraulic lifts and hydraulic brakes. In the hydraulic lift on the left, you can input a small force onto the small cylinder, and that increased pressure will be translated to all the particles in the fluid, and it will cause the particles to move down a little bit. And the result is a large force being exerted on the car on the right side of the lift, such that P out is equal to P in. So since the force increased on a small area, the force out must increase a lot more on a larger area to keep this pressure amount to be the same. Another way that we can think about this is, remember that pressure is force per area. So we could think about this as force in over area in is equal to force out over area out. Or we could rearrange that to look at the ratio of forces and say that force out over force in is equal to area out over area in. This force out over force in is what we call the mechanical advantage, and it tells us basically how many times our force is going to be multiplied within our system. So for example, if the area of the output piston here is 25 times the area of the input piston, then the force gets multiplied by 25. So if you apply a force of, say, 160 pounds on this small piston over here, the force that is then applied onto the car jack is enough to lift a 4,000-pound car. So you really don't have to apply anywhere near as much force to move something as you would without this piston setup. Similarly, car brakes work on hydraulic pistons. So the driver applies a small force to the brake cylinder, and that force is transferred to a larger piston around the discs of the brakes, of the wheels. And these discs then apply pressure. The brake pads apply pressure onto the disc, which causes friction that is needed to stop the car. So again, Pascal's principle allows us to do automotive work that we wouldn't have been able to do, that we wouldn't have known we could do previous to this discovery. There are a number of different types of pressure gauges that allow us to tell how much pressure we're applying to different places and that are used in different situations. This one on the top left-hand side is an open tube manometer. The pressure in the open end is atmospheric pressure over here. The pressure being measured will cause the fluid to rise until the pressure on both sides at the same height is equal. So in other words, for this one, the pressure will continue to rise until it is equal to P naught plus rho G delta H, where the P naught is atmospheric pressure acting at the top of the tube. Okay, so we can measure pressure once we know how much the mercury inside or the liquid inside increases its height. The center one on the bottom relies on air pressure to compress this flexible chamber here. This is an aneroid gauge. It is mainly used for air pressure, and when it is then called an aneroid barometer. And the amount of air pressure that squeezes the flexible chamber translates into motion of the pointer. Now this one on the right is a handheld tire gauge. You attach the tiny nozzle at the bottom of the bulb to the tire nozzle, and then the air in the nozzle presses on the spring in the gauge and it pushes up the scale. You then just read what level of air you have in your tires by whatever this scale reading is there, the gauge pressure. When all of these gauges were created, and when you're creating other gauges, it's important to choose a substance or substances that will have sufficient reaction to the types of changes that you can expect in pressure to get a reading. For example, mercury works really well in some cases. Water might work better in another case, or vice versa, but either mercury or water could be used to measure air pressure pretty easily. So let's take a look at how that would work. The barometer is another gauge that was developed. This picture is one of a mercury barometer that was developed by Torricelli in the 1600s, well before some other principles were discovered. This was the early understanding of atmospheric pressure. The height of the column of mercury is such that the pressure in the tube at the surface, down here, the pressure in the tube at the surface level is 1 atmosphere. So pressure is often quoted in millimeters of mercury, such that we could say that 1 atmosphere is equal to 760 millimeters of mercury. So sometimes in problems you will see pressures related to atmosphere, sometimes you will see it in millimeters of mercury. It depends on what the situation is, what measurements you use. It is important when you're solving these problems to have the correct units for all of the rest of the information in the problem, however. If we replace this mercury with water, which has a completely different density, our barometer would still work, but it would have to be significantly bigger because this pressure and the amount of height you would have to get to 1 atmosphere is dependent on the density of the object. So let's take a look at a water barometer. This is an old picture of what a water barometer looks like. You can see the bucket here at the bottom, and then the tube goes way up to the very tippity top. That's the air column in the top, and the water is about to there. Any liquid can serve in a Torricelli style barometer, but the most dense ones are the most convenient. This barometer uses water and would need to be about 10.3 meters high and would need to have a vacuum at the top here in order to work. The ramifications of this are that if we want to drill deep into the earth to get fresh water, we cannot use a vacuum pump that is more than 10 meters deep. We would need to use a series of pumps within 10 meters of each other, or the water pressure would be such that it would just flow back out the bottom of our pump. So in other words, if this were much more than 10.3 meters, all of the water in the tube would just come out and would overflow our bucket here. So it is important to remember that it is the lowering of pressure within straws or tubes that allows fluids to flow up into them and not a sucking of the fluid up into it. So again, these water pumps from deep down would have to have a decreased pressure at the top in order for water to be drawn up into it. So when we drink from a straw, we're not sucking the drink into our mouth, but rather we are lowering the pressure at the top of the straw so that the atmospheric pressure on the drink itself pushes the drink up into the straw, similar to how this water barometer works. Okay, so with this information about how gauges and barometers work, we have a much better understanding of how we can measure fluids and the pressure on them. Bye for now.